Why don't we get started here? So anyway, I for the homework this week, sorry I'm not there. I got like on Saturday, I was like all congested and I did a test and it was like solidly positive. So it's like, and it says on the internet like 5 days with a rebound. So hopefully Wednesday I'll be fine. I'll check and see if I'm okay. I didn't check this morning, but I felt still had something going. Anyway, so that recording of the class from last Friday through the homework, there's no sound until you get to 37 minutes on it. So I put up last year's lecture. Here, update that. I haven't shifted that, but anyway, this is a lecture from last year on the same, because I did the same quiz same homework last year. So that should make up for it, I guess. If it doesn't, email me and let me know if you're having problems with it. Any questions on the homework? Or you guys can hear me, right? I tuned AD. Oh, yes.
Yes, I can hear you.
Feedback. All right, that's good. All right. So sorry, that's that. So I wanted to, so we've gone through, oh, all right. And then so we can do a tour at Lyondell like any Friday, basically, but I was thinking we could do it this Friday. But the problem is they don't work on Friday, so there's not many people there. So the machines won't be running. Like they have process equipment and things that run where they do trials on different products, like huge oops, someone's not muted, but mute him. There. So anyway, so they aren't going to be running the machines. I mean, the machines will be there, but they aren't running. So basically Tuesday, Thursday is better, is what I heard. They'll be doing, they do trials on, so these big film blowing machines and pipe extruding machines and injection molders will be running like Tuesday, Thursday. So I don't know, why don't you guys, I told them that we want to do it this Friday after class. So to get there around 12:30 or something or 11:30 on Friday. Email me if you, I don't know, anyone want to comment on that? Like if Tuesday, Thursday, anytime is possible for you guys, or I think it's mostly the undergrads that wanted to do this, but
I could do Tuesday or Thursday morning, if that would work.
Okay, so like when would you want to go there? Like 10 or something?
10 o'clock. Tuesday would work a little better than Thursday.
All right. Okay, any other comments on that? Okay, so I'll see if, yeah.
We have like graduate students, I think that we have like this month Tuesday and Thursday from 9 a.m. to 11.
Wow, Yashmi, your audio is like terrible. It's like muffled, I can't understand. Can you, could you do like a type in whatever you just said? Because I can't understand it at all. It's totally muffled. It's a mic you're using is messed up. Let's see, where is the let's see, did you chat it in? If you could put it into chat, whatever you just said, I can look at it. But if you could chat it in, that would be good, because I couldn't understand what you said. Oops. All right. Well, did you, Yashmitha, could you hear me or that? I think it was you that said, right? Maybe you weren't talking. Oh, wait, here, Prof, we have lecture on Tuesday and Thursday from 9 a.m. All right, so it won't work for the grads. Okay, so let's just stick with this. Let's stick with this Friday. Okay, I guess, unless it's Carter, what about after 10? Like, oh, you said only in the morning, right? And they have 9 a.m., so it won't work Tuesday. So let's just do Friday.
Yeah, Friday, I guess Friday seems like it works best for the group.
I mean, you know, when the machines are, it's pretty cool to see the machines running, but they're really noisy, and you can ask a lot more questions when the machines aren't running. You know, so
Yeah.
maybe, I don't know, maybe we can go back or something to see them running, but it's probably just as good to do it on Friday and kind of get it over with, and then we can think maybe we can do some other tour or something.
Mhm.
So
Yeah, Friday
everyone's,
works well with me. So
all right. So let's just go Friday after class and go down there. And it's kind of during lunchtime, but I mean, we could go a little bit later if you want. It's up to you guys, but basically, you know, probably be better to just, because we're all together, then we can just go then. But so I could potentially take, if you don't have a car, we could carpool, or I could take like 3 people with me. I think that's how big my car fits, but so if people need a ride, we can try to do that. All right, so let's try to do that. That's good. Anyway, so I'm gonna move on then. So anyway, so we've done, I said there's like short range interaction and long range interaction, right? And that was decided by Flory in like 1963, I think, a book called Polymer Chemistry. So he broke it down to short range and long range. So the idea is like, if you're going along the chain and it has an index I, like if I minus J is like less than 10, you're kind of in a short range interaction mode. And if I minus J, so you have 2 units, I and J, how far are they apart? So if they're close together, short range interaction, that would be things like you can't go to a back step, or the idea of a bond rotation angle, things like that, right? And also some charge effects. So we've seen a few of those things. Long range interaction is if like I minus J is like bigger than 100 or something, or on the order of 50, something big number, right? So in that case, you're talking about what you call excluded volume. Right. So you have the idea is like you're going along and then like, oh, I can't do that. So if you're doing a simulation, you have to start out, say you're doing a simulation of a melt, like in this last week's homework, I guess. They start the simulation, they have to make chains. So they want to put all the chains, they want to have excluded volume so they don't hit each other or don't cross through each other. So then when they start doing a random walk and they get to this point, you can throw that chain away. And then you just start over and make another one until you get ones that don't cross each other. And as the melt gets denser, this problem becomes bigger and bigger. So it's a problem that they knew about right at the beginning. You said that short range interactions, the main conclusion is that this NK, LK, so LK versus L naught, the chemical unit, or L chem, like the 1.54 angstrom for carbon-carbon, this becomes like 10 angstrom, right? So 1 nanometer. So basically you have C infinity is going to be this LK, the actual step length versus the chemical step length. That's maybe on the order of like 5 to 10. For protein, it's in the hundreds, right? So some synthetic polymers. So that's kind of the conclusion, is that that the mean squared end-to-end distance is still going to be, so the fractal dimension is 2 for these chains that due to short range interaction just changes the length of the step and the number of steps. So for excluded volume interaction, the main conclusion is that this R squared isn't going to, so R is going to be N times LK to the 3/5. Okay, so this is not a, so the square root of R squared, so the root mean squared, is going to be this 3/5 power, meaning that DF is 5/3, right, or 1.67. Right, so we'll kind of develop that idea today. Okay, so how do you go from this random walk to this self-avoiding walk? So basically it's a random walk and a self-avoiding walk. They're both random, but this thing avoids itself in the process. Right, so that's what he calls long range interaction in 1963. Right, so the terminology has changed over the years slightly. Right, so anyways, that's the topic here, long range interaction. So there's quite a bit to talk about in this, and it's a little bit more mathy than the short range interaction, believe it or not. So anyway, so this idea of excluded volume. So you're doing this walk, and you find a place where you don't want to cross yourself, right? So that idea of excluded volume, Florey didn't invent that, right? That was invented by van der Waal in, I guess that should be a small v. I always get that confused. So it was invented by van der Waal, I think it's like 1890 or something, like a long time ago. Dutch scientist, Dutch physical chemist, right? And he was talking about gases. So all the ideas of the Florey, what's called the Florey-Kriegbaum theory. So I guess that means like a war tree, right? Anyway, Kriegbaum was at Duke. So Florey was Ohio State. Then he came to Cincinnati. Then he went to DuPont and worked with Carruthers. Carruthers is the guy who invented nylon, all the condensation polymers, polyesters, right? Would have won the Nobel Prize, but he killed himself. And then he went from DuPont, and then World War II happened, and he went to Cornell. And that's where he won the Nobel Prize. And then he went from Cornell to Stanford. And somewhere along this track, he got together with Kriegbaum. I think it was when he was at Cornell and Kriegbaum was at Duke. Then Kriegbaum taught a guy named June Rowe, who was a professor at UC. So June Rowe was one of Kriegbaum's students, went to Bell Labs, and then came to UC. Right. So anyway, we have a link to Kriegbaum and Florey at UC somehow through Rowe and through that Florey was here after he graduated from Ohio State. And then anyway, so we're somehow linked to this concept at UC, I guess. And anyway, so the concept, so I think a lot of these times people knew the answer before they got to the mathematics of it, and then they forced the mathematics to give them the answer, right? And the answer came from simple van der Waals equation, which was they had the ideal gas law. They wanted to say, well, in the ideal gas law, the gas atoms can just like pass through each other, right? There's no excluded volume. Right, so you have PV is nRT, and if you talk about a molar volume, then you just say PV molar equals RT. And if you want to talk about a compressibility factor, that's PV molar over RT, or you can talk about the molar density, and you have P rho RT. Right, so that's an ideal gas, right? And the idea is you can pass right through. So then van der Waals said, well, they can't pass through. So there's a volume that's excluded. So he puts in this B term, which is the excluded volume. So he invented the word excluded volume. He called it B, small b. And this increases the pressure. So you're dividing by volume, volume here. It's not molar because you have an N here. So, and you subtract off the excluded volume, and that makes the pressure go up. Right. So then that doesn't include, so what that allows you to do is get a more realistic picture of pressure. Right. So if you plotted pressure versus volume, then you get pressures inverse to volume. So you get this like swooping curve like that. Right. And then all this does, if you just include the B part, it increases the pressure. Right. So it's a bigger effect at low, and then it's going to diminish as you get closer. So that's the B effect. Right. It increases the pressure. So, but what they really wanted to do was see, so you can't get any, there's no phase separation. And phase separation is important. You want to see condensation to a liquid phase from a gas, right? So you can't get that unless you have an attractive term. So you call that attractive term A. I guess maybe A means attractive. Attractive potential. So attractive potential has to decrease the pressure. So you just put in a term minus this attractive potential that decreases the pressure, right? And the attractive potential is going to be a binary potential, meaning you have two things. So what's the probability of finding that thing? It's the density, or 1 over the molar volume. Right? And then the probability of finding that thing is the density, 1 over the molar volume. And if you want to know the probability of the two things hitting each other, that's the probabilities of each one squared times each other, right? Probabilities multiplied. So rho squared is so n by v squared is rho squared, the density squared, times this attractive potential number, right? So you notice B has units of volume, so it's excluded volume. And then this term has some kind of potential per volume squared units, right? Pressure per volume squared units, right? So anyway, so that's the setup, that's the van der Waals equation. And what that gives you is that this thing will, you can see there's a temperature term here, and there's no temperature term here, right? So as you change the temperature, as you approach there'll be a critical temperature where this thing will go nuts. So you'll get a phase behavior where you get this swoops down, and then it'll have a phase separation point like that, right? And you have at the low volume you have gas. I mean, at the low volume you have liquid, at the high volume you have gas or vapor, right? So then this is a two-phase region where you have tie lines. Right, so the van der Waals is the first thing it would give you, and it's the first cubic equation because it's a square of the density. So it's also called a cubic equation of state. Right, so anyway, this you should have seen at some point in your life, if you've lived a full life. So what do you do with this thing, right? So that's the van der Waals equation. It's got the B that increases the pressure, the A that reduces it. That's the compressibility factor. And then so PV over RT or P over rho RT is the compressibility factor. Usually you do an expansion of this, a Taylor series expansion of this in density, if you want to talk about non-ideal behavior, right? So the ideal behavior would be the first term 1, this compressibility factor equals 1 because PV equals rho RT, P equals rho RT. That's the ideal gas law, 1. And then this would account for the first order, so the binary interactions, because you have rho times rho would be rho squared. So that's called the second order Birol coefficient. They could have a third order and fourth order would account for 3 units interacting or 4 units interacting, or it can account for if the units aren't spheres. So the second order accounts for spherical interactions. And if your things are like ellipsoids, then they have this weird thing that they can interact differently in different directions. So the third order would account for ellipsoidal structures, or it accounts for 3 units interacting. It can be either one, right? Or it could be both. And then, so if you get odd shaped things, you can also get this issues of expansion to higher order terms. Generally, just the second viral is all people use. So this is an expression for pressure, this is an expression for pressure, you can set the two equal and solve for B2, solve for the second viral coefficient in the context of B and A from the van der Waals equation. You find out that B2 equals the excluded volume. So B2 has units of volume because rho is 1 over volume. So molar volume, right, or atomic volume. Right? So B2 is like excluded volume, except it includes this attractive potential. And the bigger the attractive potential, the lower the excluded volume. So you kind of mask out so the attractive potential can mask out this fact that the thing can't pass through itself. So you can say you can't pass through itself, so your pressure goes up. But you could say that if A is large enough, or if the temperature is right, then I can act as if I could pass through myself. Because at that case, you would be in this situation where B equals A over RT. So you get the magic temperature where the enthalpic attractive potential matches with the excluded volume, right? And then these things, a ratio of the two gives you a temperature, a magic temperature. That's the phase separation temperature. That's where you're going to go to liquid phase, right? So going to liquid phase means you have to have a perfect match between the attractive potential and this excluded volume. In other words, they balance each other out. They balance each other out at a temperature, because temperature is energy and A is energy. Just all goes well if you have the gas constant here, or Boltzmann's constant if you're talking about molecules. All right, so that's kind of the magic of the van der Waals equation, that you can end up with this magic temperature, right? So, and in polymers, there's also phase separation. So you want to also have a magic temperature, and you're also going to have these attractive potentials, and you're going to have excluded volume, which is the thing we talked about at the start. Right, so there's two things you kind of need to worry about. The excluded volume part is pretty easy to do, right? Or they're both kind of easy to do and kind of hard to do. In other words, it was kind of brilliant what Florey-Krigbaum did, but actually when you look back at it, they just took the van der Waals equation, which had been around in 1951 by kind of like 80 years, right? 70 years. So it's been around 70 years, this equation. They kind of figured out that's what the answer was going to look like. They sorted out how to fit it into polymers, and then they figured out what the math was to get that answer. I think, to me, that's what the sequence would have been, have a logical sequence. So that said, so we have like kind of an ideal, and then the non-ideal is made up of excluded volume and attractive potential. The attractive potential allows you to have phase separation, right? The reason it's attractive is because you want to have phase separation. And then you end up with a critical point from that in temperature, right? So anyway, so how do you go about doing that? So we have this expression. So there's a Boltzmann probability for this. Let's see. So we have this expression for our probability of the chain, the Gaussian probability. In other words, what is P for end-to-end distance R? And we said that was going to be Gaussian. In other words, 0 is going to be the most popular, because you do a random walk, it's most likely you end up at 0. And that's a decaying function, and it's a symmetric function. So the simplest decaying symmetric functions is exponential minus R squared over NL squared, with this thing being 2 sigma squared. So the standard deviation is that NL squared is R squared, right? Or the square of the standard deviation, right? So anyways, and then if you integrate that to get the integral from negative infinity to plus infinity to be 1, you get this prefactor out, right? So this is the guts of it. It's a symmetric function that describes the probability of an end-to-end chain, right? And then we want to include in that some kind of Boltzmann. So we want to include so if you equate that with the Boltzmann, say it's a Boltzmann probability to get that chain length, then you find the energy for the chain is this number, right? So the energy for the chain is just the argument here in 3D. So that's one half is in 1D. It's in 3D. Cube the probabilities is 3D, right? So anyway, this is the energy just by comparison with those, you get that energy, right? So we want to say, like, what's the probability? So what another probability you want it in the same form, so we can just add it into an exponential power. So we want an exponential form for the probability of excluded volume. So the probability of excluded volume, so say you had 1 unit of volume VC, one Kuhn unit of volume VC. So the probability of finding that Kuhn unit is VC divided by R cubed. So you're talking about, you're within a chain and you want to find these sites. The probability, the volume of that site is VC, and the probability of that thing finding it within this R size coil is VC by R cubed. That's a probability of one Kuhn unit hitting the chain. hitting the walk. Like if you're randomly walking, what's the probability the next time you hit it, you're going to hit that unit? The probability you're not going to hit that unit, which is what we really want, is 1 minus that probability, right? And then if you want to know for that's for 1 unit. If you want to know for the entire units, you multiply it by the probabilities by how many times a binary interaction of that type would be. So that would be n times n minus 1 divided by 2 factorial gives a probability of 2 things happening. The number of times that 2 things would happen. And then that's basically, if n is a big number, that's n squared by 2. So you take the probability of 1, raise it by n squared by 2, and you get the probability that you didn't cross a chain, which is the thing you want. You don't want to cross a chain. So 1 minus gives you didn't cross a chain. This is you did, 1 minus is you didn't, right? So anyway, how do you get that into exponential form? Well, you take a log of it. So you take log of this. When you take a log of it, the power goes out front, right? So you get n squared by 2 out front, log of 1 minus VC by r cubed. Then exponential of that gives back the same thing. So exponential of log is the argument of the log, right? So then you have exponential of this business. So then you do an expansion of exponential. It gives you 1 plus x squared by 2 plus whatever. So if you take x equals log of 1 plus x, forget about the higher order terms, then that log of that thing can be, if x is a small number, so you forget about the higher order terms because x is like 0.0001. So 0.0001 squared is like nothing, right? So those go away. So this is VC by r cubed is a small number. So you just take the first order term, and then log of 1 minus that is just minus that, minus the VC by r cubed. And you still have the n squared by 2. So you have an exponential expression for the excluded volume that's the same as this. So you can just add this into the energy, right? So let's see how that works. So you have this energy. So you see it's minus, and this is minus. So the minuses all go away and just have plus here, right? So the energy, so what happens when you include excluded volume? It increases the energy. So increasing energy is a bad thing, right? It's a penalty. You want to decrease energy. So this attractive interaction is increasing the energy of the system, right? In the single phase, meaning it's heading towards it's causing kind of a higher pressure in a sense. But this is similar to the B term, the hardcore excluded volume term of the van der Waal equation. So we have the ideal, which is 1 in the van der Waal, and then we have this excluded volume term, right, which is B in the van der Waal, and this number here, right? So basically that's the first step of a 2-step process because we don't have the A term, right? So we want to get the A term. Any questions on this thing? You can see it's kind of math intensive. In the end, there's just this 3/5 scaling law comes out of this, but all right. So anyway, so how do you get the other part of this thing? Well, first, before you do the other part, we'll get after, because you can just modify this VC and get the other part. So how do you get this 3/5 power law thing, right? So before, what we did, when we went through the integral of our, so we said if you wanted to get the mean square distance, then you're going to need the probability of the distance times r squared, integrate from minus infinity to infinity, and divide by the integral like that of P of R, which this thing's 1 if it's if P of R is normalized, right? So this is just the normalization factor that would be in front. So that's how we did it before. We said like P of R was exponential r squared over NL squared, right? And then we said, well, that's not possible to do that integral, but then we figured out how to do that integral by doing it in 2D and then taking the derivative of the result of that. We did that last time. So it's possible to do that integral, right? But it's not possible to integrate this thing, this r squared, and then adding in this other term 1 over r cubed. Like there's no way to solve that integral. So we can't get the average R squared by the normal root. So Flory-Kriegbaum, so what does this thing look like? So I said before, like, so we have the Gaussian, and then we multiply the Gaussian by R squared. So it's going to look a lot like that, but it's going to have kind of a bigger tail out here, right? So it'll still be symmetric, right? But it kind of raises up the high end of this thing. When R is 0, it's the same value, right? So anyway, so basically you want to integrate. So you can integrate that. I showed you how to do that, but you can't integrate this other function, this thing when you add in the 1 over R cubed, the excluded volume term to it. So in that case, you see that if you say d derivative of the probability, so derivative of R squared P of R at this curve, dr equals 0 gives you kind of the oh, I did this wrong. No, this isn't what it looks like. Sorry. Gaussian looks like that. And if you multiply by R squared, there's an R squared term is going to be going like this on the sides, right? And this thing's going down. So you end up with is a peak in this thing. And then it's got the middle and then another peak, right? So this thing gives a peak. So if you find the derivative of this R squared, no, R goes to 0, it goes down to 0. Sorry. Let me fix this. Sorry, I didn't do this before. So R squared's 0 at 0, right? So, and then it goes up, and it's got this Gaussian weighting. So that tails down. So that Gaussian exponential decay is bigger than the R squared. So that thing goes like that, right? And it turns out that if you take the derivative here, dp of R times R squared dr, that you end up with a point that's proportional, or you'll end up with NL squared. So we have exponential R squared over NL squared, 3, 2, right? The derivative of that is going to be that same term times the derivative of the argument, which is 2R, or the 2 cancels, and then 3R over NL squared, right? And then you say that derivative equals 0. Right, so you can then you can divide by this term and just say that let's see, how do you do this again? The derivative equals 0. Let's see. There's also a prefactor to this thing, right? This prefactor doesn't have. Oh, it does, because it's this thing times. Sorry, it's this thing times R squared. All right, so the first derivative first times the second. So you have 2R times this exponential thing. And then the derivative of the second, then you have plus R squared times the derivative of the second, which is the exponential thing, times the derivative of that argument, which will give you the 3R cubed over NL squared. So you have this exponential in both terms equals 0. Then the exponential drops out. And then you have, sorry, this is hacked up, but then you have 2R plus 3R cubed over NL squared equals 0, right? So that you can kill off the R's, this becomes squared. And then you have 3R squared over NL squared equals 1/2. And then you have R squared, so this kind of, I don't know, peak, the peak R squared equals 1/6 of NL squared, or 1/6 of the average of R squared. Right. So by taking the derivative of R squared P of R, you get kind of the same answer. You get 2D. So df equals 2. Right. So you get the fractal dimension is 2, which is kind of the answer you wanted, and you get some weird prefactor, so it isn't a perfect result, but you have basically the same answer that you had before, that you can do a derivative of that instead of doing the integral. You can get the same maximum, same scaling behavior in n. That was the argument that Flory-Kriegbaum came up with. So So that's what they did. So because you can take a derivative of this function pretty easily, but you can't do a integral, right? So they wrote out that probability function with the excluded volume. They did the derivative of it. Then this is a solution they got for their magic R, which would normally go as NL squared, right? And you can rewrite that in this form, this 5 and 3 power. This is square root of n here. And then you can say for large n, the R ratio is large. So this is the approximation they have. For large n, the R ratio is large. That means that the cubic term, you can forget about it. And then if you forget about the cubic term at large n, then you get that R star is into the 3/5. So that's where you get that the dimension of the thing is 5/3. Right, this is 1 over df, or they call that also nu. So basically this gives you this 3/5 power, and that's the result that they came up with. It's not Gaussian anymore. So if you say that R goes with n to the 1/2 or n to the 3/5, that means that so 3/5 is bigger than 1/2. That means that the R excluded volume is bigger. It means that you have the coil, and then you have the coil. Right, this is a good solvent. This is a theta solvent. Right, this is a Gaussian. This is an expanded coil. Right, so it gets larger, and the scaling dependence changes. So with a short range interaction, df equals 2. With the long range interaction, df equals 5/3. That's Flory-Krigbaum. Right, so that's kind of involved, but basically that gives you this the scaling difference, right? The expanded coil is a different coil. It's got a different kind of nature to it. It's not Gaussian, right? The Gaussian, this would have to be 2 or 1/2. All right, so this is how that pans out. If you write out, say, actually do the integral, right? So you can't do the integral analytically, but you can do it using a computer program. So you can actually do this integral, right? So do the integral, that's the red dots, okay? And then its Gaussian is this pink. So it's quite a bit different than the Gaussian, especially when n gets to 10,000, then you're off by a factor of maybe 5 to 10, right? So the coil's expanding by a factor of about 5 to 10 when you're a normal chain, 10,000. Okay, so at the low end, that doesn't work out well, but there's a power law that shows up. So what is that power law? If you fit it with a black line, you get 1.72 for the power law. Okay, which you get the fractal dimensions 1.72. So you have, so basically 1.72, so they talk about 1 over df, so that's df. So it would be df's 2 for a Gaussian, it's 1.72. It's a lower dimension, it's going closer to a rod, right? 1 would be a rod. 1 over df is what they call nu, and that's the number that people talk about, and that would be 0.5, let's see, what is it for that? 0.581, I think, for that, okay? They do computer simulations of a chain, do a molecular dynamics simulation, do it for 1 million chains, then you'll find out that you get sometimes 0.588, which is 1 over 1.70. So you have another option, 1.70. That's a molecular dynamics simulation. This is integral of Flory-Krigbaum. And then the Flory-Krigbaum answer is 1.67 or 5/3. Right, so you have kind of several options here. The most likely one seems to be this 1.72. But you'll see in books, they'll talk about 1.70 or 1 over that's 0.588. And for a random walk, that nu is 0.5, like a half, right? So anyway, that's the scheme of what's going on here. Like the coil's expanding, how much depends on which, if you want to believe the original Flory-Krigbaum, it's kind of an easy ratio. Things were simpler back then. So you just had a numerical ratio. Simulations, you do 1.70. If you do an integral of the original work, then you get this 1.72. So the problem with their 1/5/3 is that you're making the assumption that the ratio is large to get rid of this term, so you can get the 5/3. But if the ratio's if the ratio is large, it's not the volume change. This is all assuming that you have a perturbation of the structure, so it's small changes. Like the original thing is a small change perturbation. This ends up being a large change perturbation, meaning people say that this is inaccurate because of that reason. Nonetheless, if you do neutron scattering and measure this number, it comes out pretty close to 5/3. And you can see all these are close to 5/3. Like, so there might not be any difference between those numbers. All right, so any questions on that thing? It's kind of involved, but that's how it was done. It's basically they took this van der Waals function with excluded volume, did the derivative instead of the integral. You can get this 3/5 power. So then we want to talk about the A term, right, in the van der Waals. So the problem is this, the reason why they went after this is because if you have just 5/3 and 2, right, then you just have 2 steps to this. This is the actual measurement radius versus temperature. The theta temperature is this black line. You can see the critical point is at a point where the thing is changing like crazy, right? So it's not at a minimum out here. This theta temperature is there. And then there's a gradual increase until it plateaus out at some kind of excluded volume chain. Right, so there's no two-step process. This thing's a two-step process. You either have self-avoiding or you don't. It's like yes or no. Right? If you have excluded volume, you have this scaling. If you don't, you have that. Right. So but it turns out it's not a yes or no question. When you measure it, it's actually a gradual thing. So how do you explain that gradual thing following the Flory-Kriegbauer approach? Well, you have the van der Waals. It's got this. Also, you don't have phase separation with this. So basically, you want to have the same answer as van der Waals. So we have the B term, this term. So we have the A term ideal. We have the ideal term, the B term, but we don't have the A term, which is going to be thermally dependent, right? And the B isn't. B is just the hard excluded volume of the thing. So the temperature dependent part means that you're going to have to find another exponential thing. And the exponential thing you need for the temperature dependent part is just the same Boltzmann function, like the energy, some kind of average attractive energy. So A is attractive. So attraction between the polymer units compared to the polymer and the solvent. And then over KT exponential gives you this probability, a Boltzmann probability, or it's log of the probability times KT gives you the energy. So that's entropy, right? It's an entropic probability driven by this energy. So what is that energy? So the energy is made up of polymer-polymer interactions, polymer-solvent interactions, and solvent-solvent interactions, right? And it's attractive polymer-polymer, so you want to be positive for the polymer-polymer one. And if the solvent likes the solvent, that also makes it positive because they're separating, right? So it's an attractive that's driving separation. And then it's negative if the polymer solvent is good. Or -2, because there's 2 units for there's 2 ways to do the polymer solvent one, solvent, polymer, polymer, solvent. Right, so there's a 2 times that energy. So if this thing gets large, you get a negative energy, and that means it's a negative attractive, meaning it's repulsive. Right, does that make sense? So negative A here means you have repulsive interactions driving, the enthalpy is actually driving, like if you had charged particles, it would drive it to be a single phase. Right, the A is usually positive, leading to liquid formation. So here, generally, you'd think that this would be positive to lead to liquid formation, right? So if you have a positive delta E, and delta E is going to be per mer unit. So this is per unit, per mer unit, Kuhn unit, right? So you have the Z Kuhn units. The Z is a coordination number. So you have the say cubic lattice, so Z would be 6. So you have your Kuhn unit, and it's got 6 interactions, plus X, minus X, Y, Z, right? So it makes 6. So otherwise, Z is just some number, right? So Z is like how many coordination sites you have per Kuhn unit. And then delta E is this average energy per Kuhn unit, depending on what type of interaction. So Z times that gives you for 1 Kuhn unit, and then per KT. So this is attractive interaction per KT per monomer, this chi number. So that's called the chi parameter, or the Flory-Chi parameter. And it's a way to talk about polymer interactions. Let's see here. So anyway, how do you put that in? Well, you're going to say, what is the energy that you're going to put into that Boltzmann thing? So you have that energy, that chi energy, and in the chain there's n times chi. So we have n times chi for the energy part of this thing, and then times the probability of finding another unit for that interaction to happen, which is VC by R cubed times the number of units, which is n. So n times n is n squared. VC for the volume, chi gives the energy per mer unit, and then divided by R cubed to give the probability. Right, so that's your ER over KT, because chi already has KT in it. See, chi is already KT. So you don't need to put the KT. So you just put this number in. It's in exponential from the Boltzmann. So it's going to be energy over KT for the Boltzmann. And then what you end up with, strangely enough, is that the prefactor, this n squared VC, is the same n squared VC that we had before. And the R cubed at the bottom is the same R cubed we had before. So you just have it. Before we had a 2 here. And this doesn't have a 2. So you have a 1/2. Then you have this chi. Right, 1/2 minus chi gives you this thing. And chi again is 1 over T. Chi is the energy over KT. So this is the same form as our B over. So this is our ideal, and ideal is 1 here, and then the B is the same as this term. Right, so this is essentially, they call this a viral coefficient. It's 1/2 minus chi. It's a viral coefficient for this energy of the chain. Right, so anyway, the 1/2 is going to be the hardcore excluded volume, and then the chi is the temperature dependent part, the A part, the A over RT, the attractive potential, right? And it's negative because attraction reduces the energy, and then the repulsion increases the energy, right? So then you also have a magic temperature here where chi equals 1/2. That gives you the theta temperature where the coil acts as if it's an ideal coil. Like it acts as if it can pass through itself, even though it can't. It's because the repulsion, the excluded volume, is just overcome by this attraction, and those two energies cancel to nothing, and then it acts as if it's a random coil. So you can reach a magic temperature, this magic temperature where those things match out, and at that point you have an ideal coil. It's a theta coil, they call it. So it's called the theta temperature. It's where chi equals 1/2, and then chi equals Z times this delta E number over KT or R. If it's one polymer molecule, it's KT. And then what did I miss here? Z. This is Z delta E over KT. That's it. That's what chi equals. If that equals 1/2, then you can say your temperature is the theta temperature, and then that's going to equal Z delta E, the average delta E over KT times 2. Right, so that gives you a definition for this critical temperature in polymers, called the theta temperature. When you reach the theta temperature, the chain becomes an ideal chain. It's just like we had the T star for the van der Waals equation is A by B, right? And here we have this expression like T's 2Z average energy over KT, right? And we have this full expression for the thermal dependence of the chi is 1 over T. So this is the thermal dependence of the energy of the chain, right? So you can use that. You can use that energy. You can use that energy to calculate the coil size, and then because this energy was in the probability for the chain, use that probability to calculate the coil size, right, as a function of temperature. So if you do that, you end up with this expression for the coil size as a function of temperature. So it's got this this kind of expression R naught as the is the Gaussian chain size. And basically these lines are calculated from that expression. So it's a perfect fit. Like this is the radius of gyration, it's the hydrodynamic drag radius. So those two numbers differ because if you have a coil, okay, you'll see that the two numbers switch when you get, this is a collapsed coil. So once it's 3D, the hydrodynamic size is bigger than the radius of gyration. Because if you have a sphere, the hydrodynamic size is the radius of the sphere, but the radius of gyration is the moment of inertia is inside that. Right. But if you have a coil, they're opposite of that because the thing's spread out. Say you had a rod, right? Then the hydrodynamic size of the rod. Anyway, they switch. They switch once you get to once you have kind of a Gauss, once you have a fractal structure, Rg is bigger than Rh. And then once you have a solid structure, Rh is bigger than Rg. The ratio of those two tells you if you have a solid object or kind of a fractal open structure. So you can measure this with dynamic light scattering and measure this with light scattering, static light scattering. So you can do the two in almost the same measurement. Usually a DLS can spit out both those numbers. So it can spit out, we'll talk about how that works, but it can spit out the ratio of those two and tell you if the object's solid or if the object's expanded. So anyway, so that's kind of this whole story of the Flory-Krigbaum thing. That's about it for today, I think. The rest of this is another subject. So there's two ways. Let's see, there's something else here. There's two ways to collapse a coil. So what happens to A, so something, remember we talked about the Debye screening. So Debye charge screening. So if you have like a polyelectrolyte, with charges on it, and there's counter ions around, if I add salt to that, then the Cl minus will flood this area, and then these plus charges can't see each other, and it goes with 1 over the square root of the concentration of the salt that you put in. Right. So the concentration of the salt plus the concentration of the polymer times how many charges are on the polymer. Right. So the concentration of the minus ions gives you this Debye screening length. And there's the dielectric constant, a couple other things in here. But so basically 1 over the square root of the concentration. So as the concentration goes up, this screening length goes down, and it can get to be small, so small that there's no interaction. Right. So then the polymer becomes an uncharged polymer at that point. Right. We said it's kind of like you have someone looking for someone else in a crowd, and they can see them easily from a great distance, but if you start putting a lot of other people in the way, then they can't see them anymore. So that's called screening. So this attractive potential, A, or chi, right, has that same effect. So if you start putting other polymer chains in the way, then it can't see, it can tell there's other chains, but it can't tell in what direction they're coming from. So that's called, there's a field that comes in, but it's called a mean field. So that when it has a mean field, it can't tell the direction. It means it doesn't know how to react to it. So it basically goes back to theta state. So if you go from dilute and it's an expanded coil, then you get to the C star where you have the coil mass divided by R cubed. So then the coils start to interact with each other, and you go above C star, then you get to this mean field behavior. And if you get to a melt where the chains are just piled on top of each other, then they act like a Gaussian chain. So there's this issue. If you increase the concentration from an excluded volume situation where you have the attractive potential, and then as you increase concentration into the melt, you go to this Gaussian. So you can do a concentration to drive the contraction of the coil from expanded, which is a normal state in solution, to a Gaussian. Right. And then the other thing you can do is this temperature driven. That's basically the magic temperature number, the theta temperature, which you can get from the van der Waals equation, van der Waals approach, right? That there's some temperature where it's going to go to a Gaussian chain. It's called the theta temperature. Let's call it theta coil because of that. So there's two ways to kind of mess around with this thing: concentration and temperature, right? So what's missing from this is like what happens, right? You can see the coil gets larger and it's a gradual transition, but what does that look like kind of in a cartoon? Like what actually is the structural change that's going on? So we'll talk about that later on, but basically this Floyd-Kriegbaum equation perfectly describes that behavior, right? So we have a mathematical expression for what's going on that's based on this energy, thermal energy stuff. So any questions on this thing? Okay, so I should be in on Wednesday. Like hopefully I get a test on Tuesday. And then if I'm good on Tuesday, I'll let you know that I'm coming in. If I test positive on Tuesday, then I'll let you know that I'm not coming in. Okay, so hopefully that'll be okay. All right, so that's about it for today. Thanks.